You may not realize that proportions appear sometimes as ratios. Red to yellow is 3:2. Or equations on a conversion problem. 10 logs equals 3 dolts. Or maybe it's fractions in a probability problem. The probability of an event is 2/5. Or an age word problem. John's age is 1/3 of Zach's. Today, I want to develop a framework to solve the most basic proportion problem. Start with the simplest case. How do we set it up? How do we proceed toward the solution? And then once we've mastered that, we'll extend it to more complex cases. Because ultimately, all these presentations are the same concept at play. So by learning one concept and method, we can potentially solve a whole host of different problems on the exam. Let's start with the fundamental case, the single proportion problem. Essentially, this problem starts with a fixed ratio or proportion of things. Blue to red is in a ratio of 3:2, for example. In addition, you're usually given the actual amount of one of the items. For example, there are 27 blue items here. Or perhaps you're given a total. The objective of these problems is to use the ratio, the fixed ratio, and the amounts given to find the missing amounts of the other elements, or again, possibly the total. So how do we do that? We need to form a proportion equation from the given information in the problem. For example, a proportion equation's structure is A divided by B equals C divided by D. This is our typical proportion equation. When given ratios, the way we can do that is by essentially taking the second ratio and swinging it underneath to make it the left side of our proportion equation. So B to R becomes B over R, the number of B over the number of R, and that equals our fixed proportion. Again, swing the second part of the proportion under the first as the fraction, 3 divided by 2. So the number of B divided by the number of R equals 3 divided by 2. At this point, I know how many B's I have. The amount of B's given in the problem was 27. I'm going to substitute that amount in for the number of B's over here. Now I have a proportion equation with one variable that I can solve for, R, and it answers the question on the simple case, how many R would there be given the fixed proportion if there are 27 B's? And the answer is R equals 27 divided by 3 is 9 times 2. R is 18. If we were told the total amount of blue and red is 45, for example, we would proceed essentially the same way to start. We'd set up our proportion equation. Blue divided by red equals 3 divided by 2. In this case, I'm going to solve for one of the variables in terms of the other. So for example, B equals, after R divided by R is just 1, canceling, B equals 3 halves R. Okay, well, it's not a numerical answer like before in the last case, but now I can use this with my second equation for the total amounts. B plus R equals 45. I know what B is in terms of R. I'm going to take that and substitute the other way for B in my total equation. B is really 3 halves R. Plus R is just, well, R equals 45. Now I have one equation, one variable I can solve. And that becomes 1R, or R, equals 2/5 times 45. Well, 45 divided by 5 I know is 9, so that's 9 times 2. R equals 18. And that answers the question. How many R are there if the ratio of B to R is 3:2 and the total amount is 45? Let's look at another presentation format. In this case, my fixed proportion is given to me as an equation. like 3b equals 2r. And they'll obviously stand for something. Maybe that's 3 British pounds equal 2 US dollars. And then I'm given an amount again. I have 115 B's, maybe British pounds, if that's what the problem indicates. How many US dollars or how many R's can I convert that into? So again, we want to set up a proportion equation. How do we do that in this case? In this case, we would take the elements of what they are, the B and the R, and we'd again pull the second part under the first. So that would be B divided by R equals, and the numerical values or the coefficients of those variables will pull the one on the right down under the 3. So that would be 3 divided by 2. This would be an equivalent proportion equation for the 3b equals 2r equation. B, the number of B divided by the number of R equals 3 divided by 2. If you wanted to put that in an intermediate ratio format, we could. We would just simply say that's B to R, the left to the right, is 3 to 2. And then we do the same thing as we did before. We pull the R under the B, the 2 under the 3, and we get this proportion equation. Same concept, just a different delivery presentation. Let's look at another case where the information is presented as a fraction. Now that could be part to a whole, say in a probability problem, or it could be a part to a part, say John's age to Zach's age, part 1 to part 2, is 1 to 3. So if we know J, John's age, is 15, we could substitute that into our proportion equation. We're already a step ahead of the game of the previous presentations because we essentially have our proportion equation set up as fractions already. So I would substitute 15 for J. 15 over Z equals 1 over 3. The result is Z equals 3 times 15, or 45. So Zach's age is 45 in that case. It's almost a little bit easier. The part to whole case, let's suppose we do have a probability problem. Perhaps the probability of an event is 1/3. Okay? So in this case, 3 represents the total, not the partial amount. In this case, we're given an amount. Say there are 90 samples taken. I'd set up my equation. Part to whole equals 1 to 3. That represents, out of a total of 90, how many would meet whatever condition, be the part. Maybe it's the number of blue marbles picked out of a bag, etc. And we already have our proportion equation set up for us, and N would equal 90 divided by 3 in this case, which equals 30. At this point, we've touched upon many of the different presentation formats for our single proportion case. Basically the fundamental or basic scenario we'll run into. And we've seen the different presentations as ratios or equations or fractions, which we then convert into a proportion equation. In this lesson, we're going to look at double proportion problems. So when I see these problems, I think of that Guns N' Roses song, Welcome to the Jungle. Welcome to the jungle, da 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 da. Welcome to the jungle, to the jungle, to the jungle, da 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 da. All right, yeah, my karaoke is terrible. I admit it. But unlike that, the double proportion problems really aren't that bad. It's just single proportions that we went through in the lessons leading up to this, applied twice with some extra calculations along the way to make it work out. Let's take a look. Suppose I had 2 different proportions. A to B is 3 to 2. B to C is 5 to 4. Well, each of those I can set up as separate proportion equations. A to B is 3 to 2. That's A divided by B equals 3 divided by 2 as the proportion equation. And secondly, the B to C is 5 to 4. Well, that's B divided by C equals 5 divided by 4. Okay, well, how do I work with that? Well, let's solve for one of the variables. We aren't going to get a numerical value, and we've seen that case already in the single case, in the single proportion problem. I'm going to multiply by B on both sides, And I'm going to solve for C in terms of B. I'm going to try and keep the variable I solve in terms of the same. That'll make life easier as we move forward. So divide by the coefficient of C on both sides. And we'll see C, 5's cancel, equals 4B divided by 5, or 4/5 B. And like every proportion problem up to this point, not only do they give you fixed ratios, but they give you the amounts of one of the elements, A, B, or C, or in this case, the total amount, which is often how these problems are presented. So suppose the total amount given in this case were 99. What do we know? We know A plus B plus C, the sum of all the parts, equals the total 99. And what do I do with that? Well, A, I solved in terms of B. C, I solved for in terms of B. I'm going to substitute those values back in. So A is really 3/2, and B, well, that's just B. And C is 4/5 B, so I'm going to substitute that up in for C, 4/5 B. Now I can find a common denominator and combine like terms. Between B will equal, on the right side, 99 times 10 divided by 33, and I know 99 divided by 33 is just 3. So B equals 3 times 10, or 30. So if the question asks specifically how many B's are there, we know it's 30. And what if the question asks for the number of A's and C's? Well, we would take that 30 for B and substitute it back into either one of our original equations. And A equals 3/2 B, that's 3/2 times 30, or 45 for A. C equals 4B over 5, so that's 4 times 30 divided by 5, which is 24. Add those up, 45 plus 24 plus 30, that's A plus B plus C, you do get 99, so we can check our answers at the end as well. Let's see that same double proportion problem presented in equation format. 1.25a equals 2b, 3b equals 5c, and we're given an amount. The original amount of A's are 500. We want to know how many C's is equivalent to that 500 A's. Maybe it's an exchange problem where you convert 500 A's into C's. How many will we get? Well, the approach is going to be the same. Let's take our equations and set up equivalent proportion equations. So how do we do that? We know 1.25a equals 2b. The a divided by the b equals the 1.25, pulling the 2 under, divided by 2. That's our proportion equation for the number of a to the number divided by the number of b. Likewise, on the second equation, 3b equals 5c, I would say b, pulling the c underneath, b divided by c equals 3 divided by 5. And that's our second proportion equation. At this point, we could solve the system equations, but I like to start with the units we have, adjust given the conversion or proportions, to get to the units we need in the end. So I start with A units. I ultimately want my units to be in C. So how do I do that? I've got 500A. I need to convert the A to C. Well, I don't have an A to C conversion directly, but I do have A to B. I could multiply this effectively by B over A, which we know is the reciprocal of 5/8. So it's 8B for every 5A. And I'm going to multiply my 500A times that. The A units cancel. My resulting answer of what would be 800 at this point is in terms of B's. Now I'm going to convert B's to C's because I have that connection from B to C right here. So I have B on top, so I need to get rid of B's. I'm going to take the reciprocal. I'm going to take 5 C's divided by 3 B's. The B's will cancel top to bottom, and I will end up in units that are now just C's, which is exactly what I want. It's 800 times 5, which is 4,000, divided by 3. 4,000 divided by 3 C. So if I had 500 A's and I convert it into C's, I'll end up with basically 1,333 and a third C's. What if my initial setup is in ratios for my double proportion equation? I've got A to B is given to me as 5 to 7, and then B to C is given me as 7 to 9. The nice thing in that case, the B units are the same for both ratios given to me. It's 7. That way I know 5 to 9 is a direct proportion. And suppose the problem gave me a total of 210 items, and I want to know how many C's were in that. So I know the proportions. I could scale them. 5x plus 7x, where x is just my scale factor, will sum to 210. I have to have these proportions multiplied by scale factor to get my total. Well, what does that work out to? 9x and 7x is 16x plus 5x is 21x equals 210. X equals 10. That's my scale factor. Not my answer, my scale factor. Remember, the amounts of any given element, C in this case, is the scale factor times the proportion. So the amount of C, which is the question, is going to be 9 times 10. My proportion times my X. There will be 90 C's out of the total of 210. There will be 70 B's and 50 A's. That one's easy because our intermediate variable was the same number in the proportions. What if it wasn't given to me that easily? What if the double ratios given to me would be A to B is 3 to 5, B to C is 2 to 3. In this case, the B's do not match, so I can't quickly align them on a three-way ratio. So what do I do in this case? Well, one quick way is to put the B's over here and essentially try to set it up like a system of equations almost, with the B's matching in the columns. B to C is 2 to 3. Now my objective is to make this B number the same. How am I going to do that? I'm going to scale each by the other factor, so I get the same value for B. So for the top one, I'm going to scale it by 2, which is the other factor. That gives me 6 to 2 times 5 is 10 for A to B. And the next one, I'm going to scale by the 5 up top, the other factor, which will be 2 times 5 is 10. 5 times 3 is 15. Now you can see I've essentially set up a three-way ratio, just like we had in the other problem. It's 6 to 10 to 15, and I can work it just like the other problem. So up until now, we've dealt with single proportions, double proportions, different presentations, but the ratios themselves, the proportions have been held constant. That may not be the case in several problems. What happens if we then change the amounts of one or more of the elements or things that we're looking at? That's what this lesson is about. Let's start with our double proportion problem, where the fixed proportions are given to us in the form of two different ratios, and we're provided a total amount of marbles. So we have red to yellow is 3 to 5. How do we do this? We approach it the same way we did before. Set up a proportion equation. And if the total is 160, well, I know that means red plus yellow plus blue equals 160. I'm going to substitute my two proportion equations in, so everything's presented as a function of r. So r is r plus y is 5/3 r, given this. B is 8/3 r. There are 30 red marbles. So now I can actually put amounts. Not just proportions, but amounts. 30 red. How many yellow would there be? Well, 5/3 of 30, which is 50 yellow. And how many blue? They're 8/3. Well, given that red is 30, that would be 80 blue. Combine this 80 and 50 and 30, that is our 160 total. So these are the amounts of the different colors of marbles in the bag. This is where we left off last. Now we're going to change the number of marbles. How do we handle that in our problem setup? One way to address the change is to set up a table to organize the information you have. We'll use the colors, red, yellow, blue, the different things we have, as the columns. We know we have 30, 50, 80 of them respectively. To begin with, the rows, we're going to have a beginning amount that we've already calculated, a change, which we're going to apply given the problem, and then figure out the correct ending amount to solve the problem. So in this case, suppose we took away 20 yellow marbles. That's a change of minus 20. We didn't change the blue, we didn't change the red. So at the end, I'm going to have 30 red, I'm going to have 30 yellow, and I'm going to have 80 blue. If the problem asks me, what's the new ratio of yellow to blue, I know that answer is now 30 to 80 or 3 to 8. Alternatively, they could give me a final proportion and ask me to figure out how many, say, yellow are at the end. So they could tell me yellow to blue at the end is 1 to 2. So I could say yellow minus some number n to blue is 1 to 2. Okay. Well, I know that's also 50 minus n is to 80 blue at the end. And then I could solve that. Essentially, set up my proportion equation. 1 to 2, 1 divided by 2, that is, equals 50 minus n over 80. Solving for n equals 10. So either way, I can be flexible about what they're asking and how I solve for it. But no, one way to organize your problem and set it up for the change is to set up a table with the different things, a beginning, a change, and an end. We started with a simple fixed proportion given to us in a problem and an amount of one or all the items. That required us to solve for a missing amount. That was our typical basic proportion problem. We learned how to deal with different presentation formats for that problem, and then we added the complexity of having multiple proportions. The approach was largely the same, always finding missing amounts and solving for those unknowns. Last but not least, we learned how to organize our information to handle changes in the amounts and find any final proportions or final amounts given the final proportions. In short, this same framework can be applied to most proportion problems on the exam. So I hope this helped, and don't forget to practice what you learned. Good luck.